Hi everyone, these are videos for Chapter 2. I hope this gives you a different perspective on some of the more technical and more complicated issues in the chapter. We are studying in Chapter 2 thermodynamics, and in studying thermodynamics you might be thinking thermos, heat. And that is a part of thermodynamics, but when we talk about thermodynamics, we are literally taking the word apart, and thermo here is meaning energy, and dynamics is meaning motion. So we're talking about the motion of energy. Well, let's define energy. Energy is the property that transfers within a system in order to do work. Let's take that apart. What's a system? A system is a group of substances or objects that work together. In this case, we're talking about the atmosphere. And what are some of the things in the atmospheric system? Well, there's the sun, there is the ozone layer, there is, I'm moving down from the sun, the ozone layer in the stratosphere, there's the mesosphere above that and the thermosphere above that. And there are clouds, and there is oxygen and nitrogen and argon in the atmospheric system, and there are parcels of air that are rising in the atmospheric system, and there is the ground. So it's an enormously complicated system that we're working with, and we are transferring energy through that system at all times in order to do work when we are talking about thermodynamics. Well, what is work? Work is a force that is applied to produce movement in the system. Well, give me an example. An example of a force that produces movement in an atmospheric system is wind. Wind is a very strong and continuous force. Another one is sunshine. Sunshine comes from the sun and warms the earth. The sun does not warm the air. The sun warms the earth warms the air. Very important point in meteorology. And another example of work is cloud formation. Now, you may say, what does this have to do with movement? What does sunshine have to do with movement? What does cloud formation have to do with movement? I understand wind, but sunshine is the movement of photons from the sun down to the ground in order to heat the ground and heat the air. So we're talking about particles that are moving from the sun, photons, and they produce electromagnetic radiation. Those move. When it comes to clouds, well, what forms clouds? Water vapor forms clouds, and that needs to move off of the ocean or off of lakes and large bodies of water to become water vapor. So that is a movement. All of these are movements of molecules. This is the work that's being done in thermodynamics in atmospheric science. Of the energy that's being used in the atmosphere, there are two different types of energy. There is potential energy, which is energy that will be used in motion, but it is in storage right now, and it is being stored in this very ominous looking cloud. Now 15 minutes from now, this could be a tornado, and very likely will be a tornado. But for right now, the energy is stored in the cloud. And the energy is really catastrophic, the amount of energy. We're going to look into that. That energy that is potential, that energy that is in storage, is transferred in phase changes between water vapor in the atmosphere becoming water, or potentially becoming ice crystals, because phase changes are differences in states of matter. Water vapor, water, ice. There's a second type of energy in the atmosphere, and that is kinetic energy, which is energy in motion, energy that is moving the molecules, generally thermal energy, and we will be studying types of thermal energy, or types of thermal energy transfer, which is the transfer by conduction or convection or radiation, transferring that energy to move those molecules. You can think about it another way, the difference between potential energy and kinetic energy. Potential energy is like blowing up a balloon and then holding it sealed, and it's not moving at all. But what is inside that balloon is warm air from your lungs, which has energy, and also water vapor from your lungs, which has energy as well. It's not moving right now, it's stored. But if I open my fingers, that balloon will zoom all over the room and will release its energy in motion. It will release its kinetic energy. So at that point, when the balloon is zooming around the room, that is energy in motion, that is kinetic energy. We talk about the transfer of energy, and energy transfer is what the word thermodynamics means, the motion of energy. And we talk about what we perceive and what we see as energy in the atmosphere, and then we apply mathematical constructs to it, and we call those mathematical constructs scientific laws, and they have a lot of math behind it. This law, the first law of thermodynamics, has an enormous amount of math behind it, but we can describe the law, and it's easy to remember the description that energy cannot be created or destroyed, only transferred. Which should sound really familiar to you, because you probably learned the law of conservation of mass, that mass cannot be created or destroyed and only transferred or only conserved. And somebody might have said, well, if you have a mass of logs that you put on and that you light on fire, that mass of logs will become the same mass of ashes. And that's what we talk about in terms of conservation of mass. We conserved the mass, we saved the mass, we made sure that the mass was transferred from the mass of logs to the mass of ash. It sounds very similar to energy, and there are a lot of similarities between mass and energy. For instance, mass, as we learned, measures matter or stuff or atoms that take up volume or space. And energy moves or transfers so that matter can move and transfer. So we've got a lot of similarities between mass and energy. And they are both conserved, and they both have a purpose in atmospheric science. In this case, in thermodynamics, energy transfers so that matter can do work in the atmospheric system. Now, I can make this a little bit easier for you in terms of talking about the types of energy, kinetic and potential, in our system, an atmospheric system, and the types of work that's being done. For instance, you can do work of moving molecules, or you can do work of moving particles or photons in kinetic energy. When we talk about work for potential energy and storage, we're usually talking about breaking bonds within a substance. In this case, we always talk about breaking bonds within water. And so that can become another phase of water. Ice can become water, water can become water vapor can become water, water can become ice. Those all break bonds within one substance, H2O. The bonds in the solid are very, very stable, hard to break. The bonds in the liquid are fluid, but still very strong and very difficult to break. The bonds in vapor barely exist, and the intermolecular bonds allow gases to move all over the place as a result. So when we talk about potential atmospheric energy, we talk about breaking bonds within water. All of these units of measure for energy depend on joules. We might talk about different qualities of that energy. We might talk about temperature and heat in motion, because molecules move to move temperature, and heat is the process of transferring energy due to temperature differences. So we might talk about temperature and heat when we talk about kinetic energy. When we talk about a type of kinetic energy, radiant energy, we might talk about wavelength and frequency when we talk about energy as well. So I hope that this will help you a bit for your awareness of types of energy and types of work. Now, we call latent energy or potential energy, energy in storage. We call this latent because it's hidden. That's like lethargy. They both come from the same Latin word, lato, latere. When we talk about somebody who's lethargic, we talk about somebody who is not really moving. They're inactive. They are too weak. When we talk about a latent fact, we talk about a secretive fact in a murder mystery, a latent issue that just came up. So something that's secretive, something that's hidden, that's why we call it latent. It's usually from the Latin. And when we talk about latent energy, again, we're talking about energy that will break bonds in states of matter. And the states of matter for water are, just to review, the solid state of matter is ice, the liquid state of matter is water, the gaseous state of matter is water vapor. Water vapor is not steam. Water vapor is actually invisible. And it is a tough thing to conceptualize in meteorology because it has so much power, but it is invisible. When we see steam, that is condensed water vapor. That is actually very hot water. Steam is very hot water. It is not water vapor. In physics, in physiological constraints. Ice does store energy in its strong bonds. When it melts and becomes water, the bonds that have broken store their energy in the higher state, the water state. The water state has more energy than the ice state. When the liquid is heated with thermal energy and it gets to its boiling point and becomes vapor, the water will boil off and the vapor will hold the energy that was used to break the bonds of water and make it into gas. As such, the vapor has the most energy because it has the energy that went from ice to liquid, and now it has the energy that went from liquid to gas. Gas stores the most energy. And you can look at it in this way, that solids have energy, but liquids have more. They bounce around quite a bit more. They flow. And gases have the most energy. They bounce all over the place. See you on the next video.